I will continue with the discussion of the dye laser. Okay. So, I had spoken about the emission line width. Okay. So, the broader the line width is more and more welcome. That is because you have so many frequencies within this breadth, okay, and you can tune over all this whole wide bandwidth. Okay. So, the absorption line is in the absorption is in the ultraviolet or blue region, which excites these dye molecules, and the emission is in the visible yellow, green, reddish, those kind of wavelengths are emitted here. Okay. Now, we have to see how this dye laser I will not say, how this dye works. Okay. For the moment we are at that emission level and we appreciate that it has a wide bandwidth, so that we can have a very nice tunable laser. Okay. And if you see the structure of this line width, this is an experimental curve, of course, experimentally seen, but you can see very well that it can be fitted into a Lorentzian curve. Try to recollect homogeneous broadening, which is due to collisions, has a Lorentzian line shape function. So, have a closer look at this, you will see you can fit it into a Lorentzian line shape function. Okay. So, the dye laser broadening is due to collisions with the solvent molecules. The dye molecules are colliding with them, and in that liquid form there are lots and lots of molecules and collisions are happening, and so you have this line width. Now, we go on to see how this laser will work. Okay. So, I will concentrate on these emission lines. Okay. These are the emission lines that I am going to concentrate on. So, I will get it in this wavelength range. Okay. So, what I have done is I have excited these molecules which have gone up here, some of them have tumbled down, and then you get this emission lines. But there is a competing factor, you know, life is not that easy, there has to be some complications. So, I have these triplet states which are competing with these singlet states to absorb the wavelengths that are here. Okay. It can absorb the emission line widths itself, the emission wavelengths itself it can absorb and it can go there. And there can be a transfer, generally singlet to triplet is a forbidden transmission, but since they are not very far away from each other and the triplet state is slightly less in energy than the singlet state, sometimes the electrons flip. Okay. And all this energy or all these molecules come to this state, the triplet state. In the lasing action we do not want that to happen, but that is what a dye looks like. The triplet states exist and they start once you have you know, this sort of a inter-system crossing as it is called. Okay. So, you have some molecules here in occupying these energy levels, and they will start absorbing either these emission line widths, or it will start absorbing some of the pump line widths. Okay. So, this is the pump. Okay. So, I have to see, I have to still describe what are the pump instruments that are used to pump it to these levels. Okay. So, it will start absorbing, and if this starts absorbing, you are looking for these transition, nothing gets absorbed here, everything is getting absorbed here, you are not getting any useful transitions like this. So, you are losing out on the pump energies which are diverted here, you are losing out on the emission wavelengths also which are used to absorb, make the absorption here. So, this is kind of a competing process to our lasing action process. Okay. So, I do not want that to happen. So, we have to think of some way to avoid this. So, one way to avoid that, what people have done is you pass the dye in your dye cell very quickly, physically you replace the dye. So, each time you will have the singlet state which is on the ground level. Luckily, the triplet state does not have a ground state like this. Okay. So, this singlet state is a ground level, and your pump laser or your pump source will be able to excite the singlet states. Okay. And the singlet states emit also and non-radiative transitions also, which occur very fast in the nanosecond scale, while these transitions happen in a slightly longer time scale, maybe in the microsecond, much more than a few 50, 60 nanosecond, much more than that. So, that is like a saving grace, you avoid the population here. So, you have all the population here, they all get excited, but the moment this starts getting populated, you have changed the dye. So, you change the dye liquid or the dye solution, you change it. So, you have a new set of these molecules which need to be excited, and in the meanwhile you have got the emission lines that you require from your laser. Okay. So, that is the way you avoid it, and one way of avoiding is you have a pulsed pump. So, you have either a pulsed laser or you have a pulsed source, and the pulsing should be shorter than this interstate crossing. Before this interstate crossing occurs, you must have that pulse laser which has ended. It has come in, it can be in the microsecond range. Okay. So, you could do that. One is you change the dye physically, and another is your pumping system should be pulsed. Okay. So, these are the techniques used to reduce the influence of the triplet states. Now, let us see what the dye laser looks like, and we will come back to it again. So, you have these dye laser pumping, and the chemicals used are rhodamine 6G, which I have given as in the previous slide itself. So, you will get emission or the lasing line widths, lasing wavelengths in the 540 to 680 nanometer region. Then you could change the dye. You change the dye within the cell. You have a dye cell, and inside that you change the dye. If you change the dye to the names are really a mouthful. Fluorescein, which gives you an emission in the green region of the visible region, green wavelength. So, 536 to 560 nanometer. Okay. Then you have another dye called the coumarine dye, which emits in the blue region. So, you have a blue lasing action, which is in the 490 to 620 nanometer region. Okay. Then you have stilbene, which is in the violet region. So, you see, and then umbelliferone, which is in the 450 to 470 nanometer region. So, you see the wide range of wavelengths that are possible from the dye, okay, but not the same dye. You have to change the dye. So, so for the spectroscopist, they have to do that much work. They have to change the dye in the cell in order to get a wider and wider wavelength range. Or generally what they do is they have a knowledge of what kind of wavelengths they will be requiring or what kind of samples they will be studying. what kind of materials they will be studying, which have specifically say absorption or emission line widths, absorption I would say mainly, in the is it in the green region, is it in the blue region, or is it in the violet region. Accordingly, they will choose the dye and then fine tune it of course in that. So, they have to change the dye, but the rest of your system in your laboratory remains more or less the same, slight changes here and there. So, you have to devise a dye cell which in which you can change these dyes and the solution very easily. But and the solvents used are glycol, ethanol, methanol, hexane, cyclohexane, cyclohextrine. Okay, these are all the solvents which are used depending on the dye which you are using, the one that is a good solute for that particular dye. So, these are all the types of solvents. So, it is a kind of a liquid laser if you can see. Now, one more thing is in the dye cell, you need to do the tuning. Now, what we have seen previously is the wide bandwidth. That means the tuning is possible, but then you do not want that full bandwidth of wavelengths occurring at the same time. Okay. You do not want that. Okay. So, what do you want? You want one of those wavelengths, you want the monochromaticity. Okay. So, you have to keep elements in your lasing system which will collect that particular wavelength. So, I will be describing that. Before that, let me tell you what a dye laser design looks like. So, this is my dye cell, okay. So, where the dye is put in, and this is another laser which pumps the dye, okay, which pumps the dye. Generally, it is laser, it is not any other kind of source. But say it is a pulse laser, or it can be a CW laser too. So, this is the lasing action which is in this region, that is why I have shown it in blue, in the blue ultraviolet kind of region, and it passes through this cell. And my lasing action is taking place between these two mirrors, one mirror here, one mirror here. Okay. And this is the lambda of the dye. Okay. So, it chooses one of the wavelengths, this mirror is here, and you get an output here. So, this is one configuration of the lasing system, but there is a problem here. The problem is the laser, the pump laser is pumping along this direction, and the pumping may not be even, okay, along this direction. So, we would like the pumping to be along the direction you wish the laser to lase in. So, this sort of a pumping is not so good because some parts of the dye which is here initially, they get degraded very soon. So, degraded, and then okay, you are changing the liquid often, you are changing the dye solute quite quickly. But still as this laser starts lasing, this part gets degraded, and then along this line there is a degradation. You really do not have a good output in your lasing beam. So, this configuration is okay, but not the best. Now, the best will be like this, where you have a dye cell placed this way, you have this lasing action, and it is pumping along the line of the laser. So, it is a longitudinal way of pumping. The pump laser goes here, and then you have the dye laser which comes out, and these are the two mirrors. Now, the thing is, in this case the mirrors have to be coated in a certain way, so that that is why I have shown it in blue and red. So, this coating has to be such that it transmits this lambda pump. Okay. But the coating of this has to be, but it has to have a coating such that the dye wavelength that you require, say in red in this case, is able to reflect back and forth. So, it should have a good reflectivity for say the red wavelength, and this has a transmission for the blue wavelength, and of course, some part of the blue wavelength will come here. And then this dye, the red wavelength is going up and down, and then part of it, because this is a partial mirror, it will come out. But this is also not absolutely the ideal case, because this wavelength will also be there along with this wavelength, and then you have to put in some other elements to separate out these two wavelengths. After all, you are looking for your spectroscopic studies, you are looking for just one wavelength, and on top of that, if a pump wavelength is also added, is not what you want. Okay, you have to separate that out too. Okay. So, again this has its drawbacks. Maybe there are ways of putting some elements and separating it out, but again you are losing out on some of the energy of the red light itself in that while passing through that element, and you do not want that to happen. Okay. Okay, so, here I have just written transmitting for the pump beam and reflectivity for the laser beam. Okay, that is how these two mirrors have to be coated. The dye laser system, I call it a system because there are lots of these elements which are included with the dye cell in order to form a viable lasing system useful for the spectroscopist. Okay. Now, there can be another which is here, another dye cell. You could place it in this way, and you see this sides, these are kind of at an angle, these are at a Brewster angle. I do not know if you recollect Brewster angle, the importance of Brewster angle, which I had spoken about before, but here I give it again. The Brewster angle is defined as tan theta is equal to N2 by N1. Okay. N is the refractive index, N2 is the refractive index of the solution inside, N1 is the refractive index of the air. So, theta, when theta is tan inverse of N2 by N1. That particular theta is called Brewster angle. And why is it important? It is important because at Brewster angle, the refracted beam and the reflected beam, they are at 90 degrees. Just do a little bit of reference work for the Brewster thing. It is used in many laser systems. So, the idea of having a Brewster angle here, that means you cut the laser, the dye cell with a Brewster angle here and a Brewster angle here. So, that this pump laser travels along the longitudinal path, but it takes another path here. That is because it refracts in a different way. Okay. The refractive index of course is wavelength dependent, frequency dependent. So, your theta also will be a bit different for the blue and a bit different for the red or the lasing beam. Okay. So, it is kind of a way of separating out the two wavelengths. And Brewster, of course, it gives you a good transmission. Generally, Brewster angled cells or Brewster angled systems are used, so that you get only one polarization. They are at different angles. This is the reflected beam is totally polarized, and the refractive beam is partially polarized. Okay. Is partially polarized. But so you have sort of you have a polarized beam inside, and your reflection and transmission, your reflection and transmission is very well defined. Okay, so, this is one of the things. Here the mirror of your lasing resonator could be stuck to this stuck here and stuck here, or you can have an external mirror too. The whole idea is to separate out these two beams. Okay. So, these are some of the configurations of a dye laser. Now, see the pumping system, pumping of the dye laser. It can be pumped. The useful pumping time is limited by this I have explained even before. The useful pumping time is limited by the triplet conversion rate. Okay, remember the triplet conversion rate. Okay, so, this pumping time, how short will be the pulse, how long will be the pulse. With two linear flash lamps, a 60 microsecond pulse duration can be achieved. Okay. This is with flash lamp, not with the laser pumping. Okay. And duration can be achieved, and repetition rate of 100 hertz and an average power of 4 watt has also been shown to work. Okay. This is with flash lamp pumping. So, flash lamp has lots of wavelengths, out of which the ultraviolet and the blue part is absorbed by your dye system. Okay, so, it can be generally put in an ellipse. You have a flash lamp here, and you can have the dye cell here. And this is flash lamp. Okay. Or you could also have it like this. This is one foci, this is one foci, FOCI, and this is the other foci of the ellipse. Or you can place two flash lamps at the two foci, and you have your dye cell here. So, similar in construction, say to ND YAG or a ND glass laser, which I have described before, where you have this inner surface, which is a reflective surface. This inner surface is a reflective surface, okay, and it reflects all the light onto the dye cell. Okay. And these flash lamps are they can be longish flash lamps, okay, xenon flash lamp it could be, and then you have two of them, and you have the dye cell in the center. So, you are making maximum use of the light that you get from the flash lamps. But then suppose it is pumped by a pulsed laser also. Sufficiently short pulse durations are used, again due to the problem of the triplet conversion rate. So, it should be, the pulse should be shorter than the interstate transitions to the triplet state. Okay. So, those kind of pulses are used in the nanosecond range, shorter and shorter, which are shorter than the interstate crossing times. And some of the lasers are nitrogen laser, excimer laser, copper vapor laser, and frequency tripled ND YAG. Okay. So, frequency tripled ND YAG laser will give you somewhere in the ultraviolet, and that is the one that you need for to excite the dye molecules to the higher laser level. And continuous wave pumping is also possible, okay, which are done by argon ion laser or krypton ion laser. Now, in the continuous wave, you have to manage again that triplet rate conversion. Okay. If I go back to that slide, here. So, I do not want this conversion to take place. Okay. I do not want interstate system crossing, I do not want. Okay. I do not, and this is a forbidden state. Nothing comes down here, sort of forbidden. So, everything, all your molecules are getting collected here, and you have very few molecules for the lasing action. So, you do not want that to happen. So, pulsing is one way of reducing that, and you do not want these emissions to go up here. Okay. So, one way of controlling is by having these short pumping systems. Okay. So, short pumping system, it will quickly excite all these molecules to this level in the nanosecond range, okay, and they will tumble back here and give you the emission. But in the triplet state, what happens is these tumbling down here, they are occurring very fast in the nanosecond scale. But this triplet state, these are very long lasting time scales here. So, the molecule remain up here for a very long time, okay, before they start emitting. You can say compared to this, they just do not emit at all. They have just eaten away those molecules and kept them there without giving you any useful transition. And these are also very fast rate. So, you have to pump the laser also at a quick duration. Okay. You have to really pump them fast, very fast. So, these nitrogen lasers, they are all working at certain repetition rates, and frequency triplet and YAG is also there, and copper vapor is also at a very fast rate. Okay. So, nowadays most of the time the pulsed laser pumping is used more often than the flash lamp pumping. This was, if you can say, a traditional way of pumping. This is the more recent ones. These are the ones which are actually used. So, I will continue with the pumping of the dye cell and the resonator design of a dye cell in my next lecture.